Thank you, John. I really enjoyed your presentation. It was interesting because an awful lot of what you're doing is in fact exactly where we are. And in fact, if you saw Tom Lewis a little earlier, you'll actually see that all three of us are in the same sandbox, all trying to make connections between snap and a microbit. Ours is much closer to the Hummingbird approach, or to the Bird Brain Technologies approach, in that we started with Bird Brain Technologies, but since a lot of schools we work with in rural USA and elsewhere in the world will not be able to afford proprietary hardware, we wanted to look at providing alternate approaches which made it open source and also very low cost. The project is an NSF-funded project. It'll be in its last year from September onwards. And the intention being to add robotics to a computer science principles course. Okay, let's move on. It's Steve Holmes, are you here?
Yeah, can you hear me?
Perfect, over to you, Steve.
Oh, good stuff. I was worried about my microphone, so I logged in on my laptop. So
Steve, mute one of those.
let me kill my laptop session.
You'd mute one of your two mics, Steve.
Okay, can you hear me now?
It's probably me. Hang on a minute.
Okay, cool. Okay, we're good. We're good. Hi, everyone. All right. So I will share my screen. Is that okay, Tony? Hi, Tony. Can you hear me? Can anybody hear me?
Yes, Tony gave you a thumbs up.
Just go ahead and share your screen.
Yeah, I'll just do that. Okay, good. So, okay, I'll go into, okay, so my name is Steve Holmes. I developed the software connector between Snap and the microbit. And what this does is it allows the Snap blocks to access the I/O pins of the microbit device. So there's 20 I/O pins. Actually, there's 17. And so what the solution entails is a driver that you install on your PC here. And that allows a bridge between Snap and the microbit, which requires a hex file. The hex file is a one-off download onto the microbit. And then that allows the Snap blocks to allow access the GPIO pins. Okay, once that happens, the world of sensors is opened up to the Snap programming environment. A lot of these sensors, you know, they're 3.3 volt sensors, and they have signals, you know, between 0 and 3.3 volts. And a lot of them are under $10, and a lot of them still are under $2. So there's a lot of potential for this kit. Okay, so the driver is a quick one-click install. It goes on there on your PC, and that's it. I'm going to show you how to start it up in a minute. I'm going to do a demo, live demo. The data refresh rate is 50 hertz, so it's quite lively. There's no sensor lag. It's quite responsive. And really, at the end of the day, it's very simple. We just have analog and digital pins. So with analog pins, we can go from 0 to 1024. So we could set the voltage level. I'll go into that in the demo. And with digital, we're either turning them on and off. Okay, never mind that slide. Just mention that it was written using the C+ libraries provided by Lancaster University. It was nice code. It was a pleasure to work with. Okay, so a good thing to do to test your hardware and your software, and just to make sure everything is working before you go further, is to create a loop where we're going to send an input voltage to pin 1 from a potentiometer. I'm going to call it a rotary sensor. That's what we call it in the learning environment. So pin 1 is going to read the voltage level of the rotary sensor. And you can see that here. We're going to read pin 1, and we're going to set a variable to dial level to that value. And then here we have a LED hooked up to pin 0, analog pin 0. And we're going to take that, we're going to set its voltage level, its output voltage, to the level that we got in from the potentiometer. And so this way we're going to create a feedback loop between analog read and analog write. And that should prove that all the software is working fine. And you can see there's a very succinct way to do it. We're setting the output pin to the LED to be the input of the pin to the LED to be the input value of the potentiometer on pin 1. Okay, so if you notice, okay, I have a different slide deck, but that's fine. Anyway, I want to talk about the breakout board. So the pins are very hard to get to, right? There's 20 pins here. So the breakout board makes it very easy. So we have pins 0 through 9 here and 10 through 20 there. And if you notice, they have, each one of these has power, ground, and signal. And signal is the one we're interested in because that's how we're reading or outputting to our sensors. Power and ground can come from anywhere, and these are actually convenient to be there placed by the pin. Okay, so now I'm going to start a video. So I don't have enough hands to do all this. So what I did is I recorded this earlier. And here we go. So I hope you can all see that. And here we go. Hopefully you'll get my sound. Start making noise if you can't hear this. And I can show you that right here. Now we can go live. I've got a number of devices hooked up to it.
Volume's very low. You may not be sending it through Zoom. Maybe it's coming in your mic.
Okay.
If you go to more while you're presenting, you find turn on the sound.
Sure. Hooked up to pin 1. And I'll talk about the other devices as we come to them. And notice every pin here has a signal. Is that okay, guys?
Yes.
Okay, I'll work away then.
It's okay.
Voltage, power, and a ground. So the power and the ground are just for convenience. What's really important here is the signal coming on the pin. Is it analog or digital? Is it input or output? Okay, so now that we've got that going, let's go over how to start up the software. So after that one-click install, you're left with a desktop icon, either on your Mac or in Windows. And you can see Gobo there on my shoulder. So I'll just click on him. And the driver will come up. Now it's going to come up in an unconnected state. Because I'm not connected. So what I'm going to do is now I'm going to connect my serial cable to the device, and we're going to have a look at the boot up sequence. So there's the usually what the microbit does. And we're going to get a smiley face and a wink. And then that tells us that the device is ready. So that's a sign of health. And on the other side here, I don't know if you can see with the camera flicker, that's our 50 megahertz data exchange rate. It's always connecting between Snap and the microbit. So now what I'm going to do is I'm going to plug it into the breakout board. This might cause another connection event. So what I'm going to do is, if I minimize this and connect this, it did. So it created a disconnection event. And again, it'll take its time. So the reason I'm showing you this, if you're working with this and you accidentally knock the cable, all you have to do is plug it back in. It'll find it, and it'll reconnect. automatically. Okay, so I've got the microbit connected to the breakout board. And the other thing to note is you could run the breakout board without power, but you can't use the servos, and the LEDs won't be so bright. So it's usually good to have a power source. So the kit comes with a battery pack, which you can plug into it here. But what I'm doing for this case is I'm just taking another phone charger cable, USB cable, and I'm plugging it into the jack on the breakout board. Okay, so now what I'm going to do is I'm going to open up a Snap project. So actually, I should go through the app there. It lets you know whether you're connected to the internet or not, and it'll open up a Snap project in the cloud, which has all of the Snap libraries for the low-cost kit. But I've got a demo already planned, so I'm going to go to it. So here it is. So now we're going to focus on the rotary sensor going into pin 1. Okay? So if we go to the block library, we can see we have a lot of blocks in the sensing areas. These are all low-cost kit specific blocks. And I'm going to bring this one out just to show. So we're going to read the value of a sensor on some analog pin, right? So here are our analog pins. We've got 6 of them, 0 to 4, and then number 10. So our potentiometer or our rotary sensor is on pin 1. So what I did was I selected rotary, but you can see we support all other kinds of sensors. And the other thing we do is we support raw voltage from any sensor. That's really flexible feature, which I'll show you later. Okay, so here we are. So we're in units of percent. So we got a variable called dial level percent, and we're going to take the percentage of the voltage coming out of the rotary sensor from pin 1, assign it to that variable, and then say it as we go. Oh, I've got to enable JavaScript extensions. Yep, and now I'm good to go. And there. So now we can see the potentiometer is at 80%. And as I move the dial, we can see it goes from 0 to 100%. So this is looking good. This is a good test. All right, so that's a good test of our input voltage. So now I'm going to go to our other voltage. So we're going to take in raw voltage. So we're going to take in 3.3 volts. So again, we're just going to read the same pin, but we're going to use different units. We're going to read it in volts, and we're going to assign a different variable called dial level volts to it. And we can see there at 51%, we have 1.6 volts. That's about right. So if I go up to 100%, I get my 3.3 volts coming in. So this is looking good. We have our units in percentages or volts, and yet there's yet another value that we could use, another units we could use, and we can just read the analog pin straight. Okay, and that gives us a digital representation of the analog value. So the microbit has A to D converters on board. So it takes the voltage level and turns it into a 10-bit value, which just gets returned to the computing environment, which is a digital environment. So if we turn that on, and I turn the value, we can see that as I go to 100%, the analog to digital value is 1023. So that's the digital value for full voltage. So I go back to my slide here. What's happening is we're taking current in, the A to D converter is converting it to 10 bits, and so the highest number you can represent with 10 bits is 1023, right, or 2 to the 10th power minus 1. So we can go from 0 to 1023, and so that's how this varying voltage is mapped into the digital domain, which is required for computers. Okay, so back to the project. So we've got that figured out. Everything's looking good here. So now let's go back to our schematic and let's use the input voltage to drive the LED. So we go, that's my next loop, and we can see here, it's very simple. We're going to set an LED on analog pin 0 to the percentage of the dial, right? So we're keeping our units of percent. So if I show you that, you can see here the snap blocks are here, and we're trying to standardize with the Hummingbird robotics kit as much as possible, because many students will be going between the two kits. So here we have the LED, so we can have an analog LED, which takes a percentage, or we can have a digital LED, which is simply an on or off, right? So in this case, we're doing analog. So there I put in a variable coming from the potentiometers or rotary sensors. Now all I have to do is turn it on, and voila, there goes the LED. I'm going to the other side here, so you can see the readout and the actual physical process that's happening. So see, I can now use the rotary sensor as a dimmer switch, and I've got the data to show me what's going on the screen. Okay, so that's our loop. That's a good test. Okay, so now there's another thing we want to do is we can power more than LEDs. We'll have to save the fun for later. So that's just a demo of the basic test. As you saw there, I had distance sensors, I had servos, and I had things going on there. Also, there's the accelerometer, which is quite powerful. There's snap blocks to read the microbit accelerometer. Okay, so I'm conscious of time. So now what I want to do is just sort of end this little demo with what's on the horizon, what's new. Well, Web Bluetooth is new. So what we want to do is we want to leverage on the browser implementation of the Bluetooth driver, and that'll interact with the JavaScript environment that Snap runs in. So that'll give us a lot of benefits, as you know. We'll be able to get rid of the wire, the serial cable between the microbit and the PC. We don't have to install any driver software. So that opens up more platforms that could be supported from one instance of Snap in the cloud. So we could have a centralized instance of Snap that is good on all platforms where that support browsers that support Web Bluetooth. And it's coming. And, you know, the list is growing, you know, as we speak. So that's the new thing. So pretty soon, all that functionality we have there with that analog or the GPIO pins will be done wirelessly, so we could have autonomous robots driving around, if you like. Okay, so that's it for me. I'm going to hand back over to Tony. He's going to go over the BJC stuff.
Yeah, I think we're pretty much out of time, Steve. I know we had a slightly slow start, but we're at our 20 minutes. So I think we're probably, unless there are immediate questions we can answer now in the next maybe 30 seconds, I think the best thing we can do is upload information to the forum, you know, at the end of this session. There's a question, Steve. Does PC Web Bluetooth support non-BLE?
Does PC Web Bluetooth support non? I don't.
Yeah, it's in the chat. It says non-BLE. It's from Derek. Maybe Derek could ask that question.
Oh, here I lost the chat.
Oh, he's put a qualifier in there, Steve. Does PC Web Bluetooth support non-BLE low energy?
I don't think so. I think we're all talking about BLE at this stage.
Okay. Any other questions? Otherwise, I think we're ready for the next session to perhaps start, unless we can carry on. What happens next?